Hello, my name is Kostas. I work as the technical artist teacher at the Game Assembly in Malmö, Sweden. This video is a part of a series of videos called Getting Started with ShaderFX for Maya. And in this video, I'll be talking about two basic lighting models. That is the Lambert lighting model for diffuse lighting and the Blinn-Phong lighting model for specular lighting. So I've got a few example assets or models here, which I'll use in a moment. But before we get to those, I've just created a sphere and added a new ShaderFX shading. So I'll open the ShaderFX interface. Since I want to focus on only showing these lighting models, I don't want all of this extra stuff I get in here. So I'll just remove this, make sure you're in advanced mode to be able to do that. And I'll add my base shader, which I created in a previous video. If you're not familiar with it, you can have a look at the bare minimum shader and saving custom groups video. What it essentially does is it's the core shader nodes you need to display any kind of color on your model at all. So I can now input a color here and it should show on my model. And I think we should start with the Lambert shading model. So to be able to get the Lambert going, the two main things that you're going to need is the geometry's normal directions. So that is the vertex, world, normal, this one. So this one is going to give you the geometry normals. That is, if I were to enable showing the vertex or face normals, that's the type of data you get. So for every sampled pixel, you'll get a normal value which corresponds to either that custom normal or just the direction of the surface. So that's the geometry normal. The next thing I'll need is the light vector. We're going to compare it to the light vector. Make sure it's the light vector node you're grabbing and not the light direction. They're easily misplaced. These are, I think basically they are just the opposite direction of each other. This one is actually the direction your light is pointing. That is, if for this direction light, it's a vector pointing leftwards as the light is showing. The light vector, however, is a vector from the point that is being lit to the light. So that is the opposite direction in this case. So if you imagine this light hitting any given vertex point here, and then you draw a vector from that pixel towards the light. So no, they're not the opposite of each other. This is always going to be the same for any sample pixel actually, whereas this one will differ depending on which pixel is being sampled. Either way, you want the light vector. So the next thing we'll want to do is we need a dot operation or dot product. So I want to connect the world normal and the normalized light vector. And I'll get to what this actually does in a second if you're not familiar with the dot operator. I just want to first connect it to have it showing the result of it. I will also want to add a saturate node. Now saturate, I mentioned that node in a previous video. It's one of the more commonly used nodes that I use. And what it basically does, it's the equivalent of the clamp node, which you might be more familiar with. It's similar to clamp, or it's the same as clamp, but fixed to 0 minimum and 1 maximum. So if I were to use clamp instead and set the minimum to 0 and maximum to 1, I get the exact same with the saturate node. And this one is cheaper in terms of calculation. So if you're wanting to clamp, to not go below 0 or not above 1, I use the saturate node. So lastly, I'll want to show this as color on my object, but this is a float and the pixel color wants a float for an RGBA value. So I'll need to construct this color. So since I just want to show the results of this so far, I can just go ahead and plug this into red, green, blue, and I'll leave the alpha unchanged. So if I have a look at what this does and hit number 6 on the keyboard, actually number 7 to use all lighting. So now I'm using this light. And you can see the results here. So what this does is, the dot operator dot operator here compares two different directions. Those directions is the world normal as mentioned, or R, and the light vector. And the light vector, remember, it's a vector pointing from the pixel towards the light. So as the light hits on a pixel here dead ahead, it's going to compare the vertex normal, and the light vector will be pointing in the same direction. That is going to give you a value of 1.0. So in the event of both vectors in the dot operator pointing in the same direction, you get a result of 1.0. That's why we have this fully lit. In the case where you compare the light vector to the vertex normal here, or the normal of the object, where they are at 90-degree angle, you get a result of 0.0. So that is exactly where the light terminator line is. So I'm gradually getting from 1 all the way down to 0 here when you compare these two angles. And lastly, if I compare two exactly opposite angles, like comparing these two to each other, you get a value of -1. So +1, 0, and -1. So the reason I wanted to add a saturate node is essentially to make sure that all of the dark side here is 0.0. If I did not saturate, I would gradually go from 0 here to -1 over here. So it's basically that simple to add the Lambert diffuse calculation. One thing to note is that the vectors can have different lengths. So these three vectors, which could all be, say, a light vector, all point in the same direction, right? You can see that they're aligned and pointing in the same direction. However, they have different length. And depending on their length, you will get different values when you feed them into a dot operator. So for the Lambert calculation or lighting model, you want to make sure that you have these vectors normalized. What that means is normalize is a operator you can use that will make sure that these are unit length. That means that they are exactly 1 unit in length. 1 unit. So if I were to take this vector and run a normalize on it, it would rescale the vector to look like this one. It still retains the same direction, but the length is 1. Same with if it's smaller, it will scale it to be longer, to be exactly 1 in length, but you retain the same direction. So for all of the vectors you want to use, or all, there's 2 of them, both the normal and the light, you want those normalized before you do the dot operator. So that's why I chose the normalized one here. This is actually the same output in terms of direction, but this one might have a different length or a variable length. This one will always have a length of 1. And the world normal coming from here should be normalized as well. I know by experience that it should be. At least I see one normalized here. Not sure if there's, oh yeah, see that one of the very last nodes before it's being passed out as an output is normalized. So this one is also a normalized vector. Right, so that's it for the Lambert part. I can hit number 7 again to show all lights. So next part is doing the Blinn-Phong Specular. And for that, I actually ended up adding a few example images because it's a bit more complex. It's more of the same, but still it can be a bit abstract. So I wanted to just go through these images to give you a better grasp and understanding of what's going on. So here's a case A. This black line here is my surface, a polygon surface. It has this normal direction. Here's my view vector, or like camera vector if you will. And here is the light vector. Now in this case A, you have that perfect exact scenario where you're going to get full specular intensity. Since the light is going to go here, it's going to reflect off the surface in an outgoing angle which is mirrored across the n vector here, which happens to be exactly the same as the view vector here. So with this eye, you'd perceive this point to be full specular, if you will. In case B, I've changed the angle of the light. So now we don't have that perfect scenario where we get full specular. In this case, you'd get this one here, bouncing here, and then it would probably reflect something like that, right? But we're still fairly close in terms of angle towards the light. So we will probably get some amount of specular nonetheless, but not that intense. So in order to calculate this, we first need to make sure that all the vectors involved are unit length. That is, they need to be normalized. So in this example, I've set the L to be 1 unit length, and then I rescale the N and V here, or I don't, they get rescaled as I normalized them. After that, you add together the L and V vector. That is, this vector and this vector, you add those together. And when you add those together, you can visualize it as you take one of the vectors and place it on where the other one ends. So if this one begins here and ends over here, this one begins here, ends over here. So I take this one, the beginning part of V, and put it where the end part of L is. So it will go like this. When I've done that, I can then draw a new vector from the start of L to the end of V, and that is my new vector that I get by adding two vectors together. This new vector is referred to as the half vector, and h as a half vector, and also the half vector needs to be normalized. It happened to be almost 1 unit length, but not exactly, and depending on your angles here, your new vector as you add it together might be really small or really long. So you need to make sure you normalize it, which was step 7 here. Next part is you get the dot product between your new half vector and the surface normal. So you compare these two angles, and you can see that they're both almost pointing in the same direction, or at least fairly close, which is going to give us a value, if you remember from the Lambert example, fairly close to 1, right? If they point in the same direction, I'll get 1.0. If they point with a 90-degree difference, I'll get 0.0, and complete opposites minus 1.0. So this is fairly close to 1.0. And lastly, after I do the dot, I will want to saturate the result because I don't want the negative part, same as with the Lambert, and then also add a y exponent here, a power of by y. And you use that y value to set the spread of the specular, the width, if you will. So with a very low value, you get a really wide specular, and as you increase this value, the specular will tighten and look sharper. And here's the HLSL code for the entire formula, if you will, or equation that I've gone through here. So let's try creating this in Maya and see what it looks like. So first step was to compare the light vector with the camera vector, or not compare, add together, right? So I need to get the camera vector. I already have light and normal vector. And if you remember from this one, you needed to make sure that these are normalized as well. So we need those normalized. Fortunately, I know for a fact that they are already normalized here. Even the outputs specifically say normalized, so I don't need to take care of that. I can just go ahead and add these together. So I add the light vector plus the camera vector. I would now have the new half vector, this one. I have that one. I now need to make sure that that one gets normalized. So that I need to handle myself. So I'll go ahead and type norm, and I find normalize. So now I'm sure that the new half vector is 1 in length. Next step is to dot between this new half vector and my surface normal. So at this point, I might start to reorganize this a bit to make it a bit more easy to see. So this is my Lambert part. This is going to be my specular part over here. And I've now gotten to this step where I've got the dot product between them. The next two steps is to first saturate and then power of function. So dot product, right? Dot will give me between the range of -1 to +1. I want to just get rid of the minus part. So if I saturate, I'm essentially clamping between 0 to 1. And then lastly, I want a power of node. so. Once again, need to give myself some more space. And let's create a float to use for the power of. I connect that to the Y part. Keep in mind that the order is crucial here. You can't swizzle these around and expect the same result. It's x raised to the power of y. So this one, if I want to expose this one to play around, I could call this specular power, as I discussed in an earlier video, or spread, which might be a bit more descriptive for an artist, I'd say. So I'm going to go with specular spread, and I'll hit expose as material input so I can access it outside of the ShaderFX interface. Lastly, I'll want to show this as well, and if I wanted to, we could at least, to start with, just show it without the diffuse component. And if I now minimize this and we have a look, this is what my specular looks like. That might at first glance look similar to the Lambert, but see how this behaves. It's floating around on the object to indicate that it's view dependent. And beyond that, you might wonder, it might not strike you as a specular highlight at first glance, even if you see it floating around like it. And that is because it's super wide right now. A specular spread is really low value in this case. If I push this to say 100, this might be more what you imagine when you think of the term specular highlight. So if I rotate the light around, this is how the specular highlight behaves. And if I switch up the camera, this is what I get. And of course, you could definitely go higher than this, depending on how tight you want this to be or how wide. If I add another 0, for instance, 1000, I get this. If I add another 0, it starts getting really, really small. Or maybe I do want a wide spread. So you could say, for instance, either have this as a constant value exposed on your shader, or maybe you want to map a gloss texture or roughness texture, something similar, to have different specular spreads on different parts of the model. So if I wanted to lastly show both of these and combine them, I'd simply just add them together. So if I put an add, so, and like so, and then I could output this. Let's see what that looks like. Oops, not the alpha. So this is what I have. And since I don't have any color component other than the lighting contribution in this case, it's basically disappearing into the already fairly white diffuse part. So I could, if you wanted to, the next part, but that's not actually a part of, say, the Lambert and Blinn-Phong per se, but I'll just show this as the last thing I do. You could multiply in, say, a specific color and specular color. So I'll go ahead and grab 2 color nodes. Let's get the RGB part here. Actually, no, it should work. I was afraid that I'd already set the output to be float since I connected float first, but that actually worked. So ShaderFX actually takes care of and allows you to multiply a float 3 by a float. So this one has 3 values RGB and this one 1 value, and it's simply going to take that 1 value and multiply each component individually. So now I'd need to grab a new add node, because sadly, if I do this, it's not going to, oh, it does. It's not, it does if you actually disconnect all parts, I think. But if I were to just disconnect, say, something like this, it's still locked to be a float over here. But if you disconnect all parts of it, it reverts to accept any type of data. So I could now grab this one, and then I could plug it here, and that should work. Lastly, let's expose these new colors. So I'll expose this one and leave it as color. I'll rename this one to specular color and expose that one as well. And then we could have a look at what this gives us. So I can now set a different color for the color component, say a red. And this one I could set the intensity by doing this actually, or I could actually also add a custom color if I wanted to, but I'll stick to white. So now I can a bit more easily distinguish between the diffuse part and the specular. And once again, spread value will sharpen or widen that specular highlight. So that's it. That's the Lambert and Blinn lighting models, and basically that's the most, I think, the most basic form of diffuse lighting and specular lighting you could add. So I hope this has been helpful. Thanks.